fact of being run over with students.
Probably want to wait until there's
More than one person in the room besides the speaker. So I know that multiple people are down meeting with our candidate right now, so they'll probably be walking together up here. 4 or 5 of them there.
I just sent you an email about it.
Yes, we'll be presenting a data point. So it's a little less in depth in the chemical side. We're going to present data behaviors in
Yeah, if they
totally more depth results. So, I think there something close, but there's not very much at the moment. That is actually processing from all 3 of them. We only have about half of the data. Today it's 2 years study, about a year's worth of data. And for
What is all?
1 year's.
They're a rap group.
Really?
Yeah. Have you heard of Tyler, the Creator?
But I'm too old now.
got my bag of rotten tomatoes.
Yeah, you'll have to listen, take a listen.
So you're off the hook.
Tyler.
Yeah.
So is this unusual or was it like this last week?
Last week there were 2.
Yeah.
But there were a bunch of people on Zoom.
Yeah.
But then I forgot to unmute. So everybody was happening.
Are they able to see the presentation pretty well? Because when I tuned in on Zoom one time, it was kind of blurry.
Through the doc cam or the actual screen share?
I think the screen share,
I don't know.
or maybe the screen wasn't sharing and it was just the ring.
I don't recall which there were, but there were a few presentations where the screen was shared through that camera up there. So
Yeah.
it was zoomed in.
Yeah.
Yeah, so now I'm presenting the screen itself. I couldn't actually get the camera working. So
Well, yeah,
Okay.
so if the presenter doesn't hit share screen, then you can hit that camera.
Okay. Yeah.
Really hard to see.
I'll have to remember that.
that's fine. Right, that's fine.
Your defense on the 6th of June or the 9th of June? The 9th, okay, that's good. I'm back in the country then, so
Okay, perfect.
I just recently booked a flight. I forgot for a second, am I gonna miss it?
Oh, yeah.
The
Where are you
defense-
going?
Slovenia, for
Nice.
conference.
Very cool. Is
Yeah.
Is Lek going to that too?
No,
He's
not
going
that
to
I know.
he's going to something overseas too.
He might be going there a different time than I am. Mine's the wood protection conference, so. I don't know if Fleck's gonna, IRG, yeah, so I don't know if Fleck's gonna go to that one, but. I doubt it.
I haven't seen anything to concur on.
Yeah.
So I'm gonna give my spiel real quick and then you can move on. So recruiting days is coming up next Thursday. If you don't know, our undergraduate population is way down, and so we have a bunch of industry people coming, and it's important to have people there to actually interact with them. So I'm asking you personally, can you please show up and go through the process? Even if you're not looking for a job right now, they might be valuable in the future. And I know a couple of you are at that stage where a job might be important. So really like to see you there.
What time on Thursday?
So the presentation started at 4. maybe in this room, I forget, but it's in an email to you. So there's 3 different companies that are presenting, and then there'll be a little bit of downtime, and then the round robin that we're taking. We didn't do it, gosh, you probably haven't experienced it, right?
No.
Yeah. COVID,
Yeah, it's fun.
thank you.
All right. Well, our speaker today, as you can see, is Skyler. He's a true Oregonian, born in Lebanon, grew up in Oregon City. And he got his undergrad here at OSU with a major in microbiology and a minor in chemistry. Good job. And he came to grad school here. Wants to, when he graduates, he wants to get into the wood preservation and treatment industry as an analytical chemist, but eventually get back to microbiology, looking at bacteria, fungi, and bioremediation potentials of those things. He likes bicycling, tennis. He's going to talk about his thesis work on creosote treated posts.
All right, hello everyone. Thank you for showing up. I appreciate it. Good to see your faces. My name is Skyler Foster. I'm a graduate fellow in the lab under Jerry Presley here. And I'll be talking about the migration of creosote components from creosote treated posts.
Hit record, please.
This should be recorded. Okay. Now, okay. All right, so what is creosote? It's one of the most widely used wood preservative chemicals. It's been in use for over 100 years. One of the oldest, most commonly commonly used for railroad ties. About 70% of all creosote is used for the treatment of railroad ties. Another 20% is used for the treatment of wooden utility poles, and a very small amount is for marine pilings, which is another semi-common use of these. And this is a very important treatment chemical because it protects vital infrastructure. Rail transport is one of the backbones of our economy. As we know, it transports a large amount of goods very effectively. And utility poles, we use those for telecom poles as well as power lines in some of the older applications. And making sure that these are stable, sturdy, and long-lasting is a very important consideration when trying to protect these types of infrastructure. So creosote has many different compounds within it, over 1,500 that we know of, and this continues to increase as formulations change. So it's produced via the distillation of coal tar. And at the bottom right, there's a figure here that you can see that has it has a simplified infographic of the process that occurs from producing the coke that you see at the top right. It's powdered, burned, and then the coal tar at the bottom of the vial on the far right there is extracted. And the variation in formulation comes from the time of fraction that you pull from that coal tar once it's distilled, as well as the temperatures used. So you can get varying degrees of effective compound or treatment solutions based off of how that coal tar is distilled. Approximately 85% of the compounds, 85% of the 1,500 compounds of creosote are polyaromatic hydrocarbons, which it's a very diverse range of compounds. They all have a very similar cyclical structure. Some being benign or the effects unknown due to how many there are, they haven't been studied, and some being very toxic, mutagenic, or carcinogenic. So it's an excellent wood preservative because of that. Why? Because it's extremely toxic. And due to it being an oil-borne preservative, it tends to last a lot longer in its treatment applications, where water does not easily flush it away. The EPA has defined 16 of these 1,500 compounds as priority PAH pollutants due to their excessive ability to be carcinogenic, mutagenic, human or environmental toxins. So why are these chosen? Because of the ease of using these as a proxy to measure the relative toxicity of the pHs. So these pHs never occur, or extremely rarely if they do, these never occur in singular compounds. They always occur in mixtures of compounds. So understanding the variability and toxicity between the components can help you understand the relative toxicity of the compounds that you see based off of the concentrations of each of these. So I labeled in the box up there to the right, the black box are what we consider light molecular weight pHs, which tend to be more volatile, and the ones below are the heavy molecular weight pHs. Difference being the number of rings primarily, of course, and then the orientation of those rings within the structure. So as I mentioned, these light molecular weight pHs, the 2 or 3 ring pHs, are more easily volatilized, meaning that they prefer or have an affinity to entering a gaseous state. So these will off-gas off of a tar solution and make their way into the atmosphere. They tend to be less toxic than their heavier counterparts, but this isn't always true. And because of this, because of their smaller size, they tend to be easier to break, though the heavier molecular weight pHs are also susceptible to UV degradation. I've highlighted 2 of the pHs here that are the main focus because they make up the largest fraction within creosote, the creosote formulation that I have been using for my my study. So naphthalene is just the most basic 2 rings, and phenanthrene is fairly similarly basic, but with only 3, no complex ring structure here. So these heavier molecular weight pHs, as I mentioned, are much more toxic, and they have a higher affinity for soil and sediment binding, and this trend increases with increasing amounts of organic matter within soil. So this leads to a persistence that can last for decades, given ample conditions, lower temperatures, lack of UV light exposure. And what makes these exceptionally dangerous is they can stick to particulate matter in the air that comes from primarily vehicle smog or other sources of particulate pollution. These heavy molecular weight pHs bind to these particulate matter, which can then travel thousands of miles through the air, given ample conditions. So the source, or the spread rather, of these pHs can be very wide. And this is the reason why these have become ubiquitous environmental pollutants, which is the main reason why these are important and studied. These heavy molecular weight pHs here that are shown, each of them have a relative abundance about less than 1% in the creosote formulation that I'm using. Individually, each of them less than 1%. This is important because traditional creosotes that were used tended to have a greater concentration of these heavy molecular weight pHs, therefore a more toxic solution, whereas modern treatment solutions tend to have a lower abundance of these heavy molecular weight pHs and a higher abundance of the light molecular weight pHs. All right, and this is really why it's important. In addition to the environment or the atmospheric pollution that goes on, the creosote itself is a lighter or more dense than water. So it will sink into the soil given a point source such as this, and can make its way into the groundwater and have a dissolved plume that can travel potentially miles as well, given a large enough aquifer and groundwater movement. These can readily penetrate the groundwater and then travel and then arise in other locations. In addition to this, these light molecular weight pHs, as you can see in the top left by the house there, the vapors can then come back through the soil and off gas or sieve the top layers of soil. It's less common, but it does happen where these volatile compounds will actually congregate in a basement or subsurface areas within a building and create chronic exposures to these pHs where you otherwise wouldn't expect them to be. Excellent. So now, those are the reasons why it's important to study these pHs. They're toxic. They can be very detrimental to our own health and to the environment. So in order to assess the migration of these priority pollutants there's going to be a three-pronged study that will be enacted to test the migration through soil and through water. And a third study will be used as an in-lab control to compare and hopefully, or to compare the field scale soil test to the lab scale soil test. The three-faceted study, as I mentioned, involves firstly a lab scale barrel test where posts will be fitted in or installed into 55-gallon drums to assess the migration. The second is a freshwater pond field study where posts are installed in a very slow-moving pond or river to assess their migration through the water column as well as their fractioning vertically. Same with all studies, so we're looking at horizontal and vertical plume migration. And thirdly is a soil field study where posts are buried into natural soil and assessed in a similar manner to compare to the soil barrel test. For the first two tests, we had two different soil types because, as I mentioned, there's a trend where greater organic matter content within the soil will allow greater affinity towards these heavy pHs and light ones as well, but to a lesser degree. So two soil types were analyzed. I'll be only showing data on the one because I feel this is more akin to the natural environment we find. We don't tend to find very sandy soils, especially around here. Here is the first study where I have a 6-foot post that is put into a 55-gallon plastic barrel or drum. There's 6 inches of soil at the base or on the very bottom where the post is then planted on top of. It's backfilled in up to a height of about 2.5 feet of soil. And half of the barrels are filled with high organic matter soil, half of them are filled with low organic matter soil. In addition to that, we're using two different species of wood. We're using Douglas fir and we're using a southern pine species to compare the differences between the species due to their differences in ability to retain the treatment that we put into it. In addition to this, we're also using 2 untreated Douglas fir controls. We do not have access to the southern pine poles or untreated poles due to regulations on importing untreated southern pine. And here is a picture of the cores that I pulled, the samples that I obtained from these barrels. They are 18-inch cores that I will fraction into 6-inch sections, an upper, middle, and a lower section. And I will retain these and homogenize the 6-inch sample within itself to create a bulk average pH content or concentration once we analyze this. So you'll notice here that in the left picture, the soil core has about 6 inches of soil in there. And for this study, as you can tell in the right picture next to it, the soil is very loose. After the addition of water to the barrels to about 20% moisture content, that water quickly settled, and due to the lack of movement of water throughout the barrel, the upper layers tend to be relatively dry. I shouldn't say very dry, they tend to be relatively dry, which make it very difficult to pull an entire 18-inch core out of these. So typically 6 inches at a time, down to a depth of 18 inches. And on the far right is a figure of the general sampling scheme, just alternating the sampling site to prevent any disturbances to the future sampling sites that we'd like to have. The second study, freshwater pond field study. As you can see, we have some posts installed 2 feet into, or about 1 or 2 feet into soil, and about a 4 to 6 foot deep river. It is highly variable depending on where in the river or the stream the depth is, but they are all sit in the water column about the same amount. So these yellow arrows are pointing to metal T-posts that I have 3 different heights of sachet, or 3 different heights collecting pHs discharging off these poles. And I'm using a soil sachet method where these plastic polymer sachets with 50 micron hole or micron openings are used to capture any of the pHs coming off these poles. And the affinity, as I mentioned, using the high organic matter soil should ideally bind these pHs. As I mentioned, I'm using 3 heights just at the water surface, the water column itself in the center of the water column, and the sediment layer at the bottom of the water column. So you can see over here, you can't see this one here. That's okay. There's the 2 different distances. We have 1 foot and 3 foot that you can see away from the pole. But really, an issue that I ran into with this study is the bottom, about a foot of the sediment layer at the bottom of the river is very, very loose matter. And it's not very amenable to installing posts into it. So as you can see, or you might be able to see the T posts with the yellow arrows indicating that they seem to be slightly off I guess, non-linear towards a singular direction. The intent was to line them up with the outlet of the river. There's an outlet shorter down the way, but this isn't always possible. So this is a variable that will contribute to the variability that we'll see within the data. And here in the bottom middle is a picture of the soil sachet that I added to give an idea of what we're looking at here. These are heat sealed and can be easily transported to and from the field. Once sampling occurs, they go in plastic bags, so we don't lose any extra small particulate matter during the transport of these samples. As I mentioned, the water is very slow moving, which makes the migration off of these poles relatively low, as you would expect with a greater amount of water flow to actually increase the amount of components coming off this pole to a degree. So as I mentioned, they're difficult to install. There's some offsetting here. And also I wanted to point out in this picture here, you might be able to see the posts in the front or closest to the bottom of the picture are all pine posts. And I have the other set on the opposite side of the river there to prevent any cross-mixing of pHs between the 2 species. They're in line with each other, but with 6 feet in between poles to ideally prevent any contamination between the samples as well. As I mentioned, it's very slow moving. We've been taking water velocity measurements every month to get eventually to be able to calculate an average concentration within the water over time. And this will be very important, trying to relate this data to EPA regulations, because these regulations, it's important to understand the concentration within the water rather than the soil sachets, which is a proxy to figure out this information essentially. So the final study is a field scale study that is soil. As you can see, there's 10 posts here that are alternating species with 2 uncontrolled Douglas fir posts at the far back of that picture there. For the first sampling period, we only did a 4-inch distance sampling or core taken from these poles to gauge the relative amount of migration that we would see. Every other sampling since after the first has included a second 8-inch sampling location as well. So this soil or this field site is actually located at PV Arboretum, which is about 25 minutes north of Corvallis. And the soil there has a very high clay content, which makes it very difficult to pull cores out of this wood. And even more difficult to homogenize the samples when the clay does not want to mix with itself. It tends to stay in clumps and is not amenable to mixing very well. So this is the consideration when understanding the data from this study, and measures that have been taken, usually with the addition of extra homogenization methods that we use to hopefully mix it as well as possible. And I also did want to point out the picture orientation gives it a little bit of a skew of perspective here. I just wanted to show that there is actually a downward slope following the black arrow, where the untreated samples are actually slightly elevated compared to the rest of the samples to ideally prevent any water flow to cause any excess intermingling between the controls and the treatment samples. Here on the far right, I have a figure that is illustrating the sampling scheme or mechanism. I'm taking a 4-inch core and an 8-inch core. Doesn't necessarily look to scale, but it's 4 and 8 inches. I'm taking an 8-inch by 1-inch core, same with my other study as well. And these are similarly split into 3 sections, homogenized and retained for pH analysis. And finally, another picture just to make it a little bit easier to see. 2 untreated controls and an alternating sequence of pine and Douglas fir, with the direction uphill being north, west, east. Perfect. So once all my samples are taken from any study, they're immediately put into a -20°C freezer to prevent any temperature degradation effects to the pHs that may be within. And of course, in a freezer, so you're not getting any UV light. So an excellent way to prevent any degradation between analysis and leaching analysis. The sample preparation includes homogenization of the soil multiple times to make sure it is, especially the clay soils, because it is very difficult, as I mentioned. And because of this, or because of the 3 different soil studies, there are thousands of samples to be extracted, which makes this a fairly large study and amount of samples to actually extract and analyze. So I'm going to quickly go over, or briefly go over my extraction process, not too in depth. Really, it starts out with the soil that are in, so the soil single sample that I have 3 10-gram subsamples taken from that, each individually extracted. So I have a replicate of 3 for each sample taken. And then for the sachet, the feel of the pond test, I actually extract the sachet material independently on its own, only once, we only have 1 sachet. Because the polymer actually has a variable affinity to binding different pHs. So we like to pull off any pHs that may have bound to the material itself rather than passing through and binding to the soil. In this picture, it looks like they're going into the same tube, but they actually are separate. So we're adding 20 mils of a bridge solvent. We're sonicating it, which means just mixing it, agitating it using an instrument or machine. We're adding cleaning salts to remove any organic impurities that would interfere with pH analysis. We're centrifuging it again to retain the supernatant within the assimilation vial. The supernatant is then going to be concentrated from about 10 to 15 milliliters down to about 1.5 to 2 milliliters. And this is ideally to increase our extraction, or not our extraction efficiency, our detection limit on our GCMS, as it is the components within aren't specific for pHs, so it has a little bit higher of a detection limit than we would like. So after this concentration step, we take a 1.5 milliliter aliquot into a solid phase extraction tube, which is another cleaning step to remove any phenols or other organic acids. And then we take a 1 ml aliquot into an autosampler vial. You see the amber vial on the right there. And this is what we'll be shooting through our GCMS. So now to look into some results. I'll warn you ahead of time, they're not that exciting. And I say that because we're not detecting very much. Partly due to our detection limits, we're actually a lot higher than other studies or other labs. And between all the studies, we're having a very similar trends. There is a few outliers, but in general, there's no significant trends that we're seeing yet, and not a lot of statistical differences from the controls. There's a few things I'd like to point out, but I will point those out when we get there. Oh, and a quick example of some issues that arise when it comes to pH analysis. So you don't have to really know what's going on over here other than we see 2 peaks that are separated. That's great. That means we can easily analyze and identify the compounds within. But when we have 2 compounds that are very similar, like benzoate, anthracene, and chrysene, 2 of the priority pollutants that I'm analyzing or looking at, they actually butt up next to each other, and it doesn't create a clear distinction between peaks. So unfortunately, what has to be done is combine the 2, and we lose the resolution between pHs. Not necessarily making or breaking this experiment, but this is just a note I'd like to point in. Eventually, these are all going to be a lumped pH figure anyway, so not necessarily a large downside to this. So any compounds, as I mentioned, we do have a low or relatively high detection limit, which sounds like a good thing, but it's not. Anything below that detection limit, we actually set to half of that limit, which is a standard thing to do by the EPA. This is because we can't really say for certain whether there's 0 compound here or it's right below the detection limit. So we average it into the middle, and I will show there's going to be some asterisks on some of the data where the data, it looks like there's compound there, but that's actually just a BEL divided by 2. So there's actually, it's more likely there's nothing there or very, very, very little. That is more likely than it being at the detection limit itself. So common trend here is not a lot's going on. You don't see a large difference between depths. You don't see a large difference between species. And actually, let me preface this with saying this before I say this. A 1-year study, this data is from 3 months, but I have up to 6 months here. A few years is actually a very short amount of time for creosote migration. So this study, for you to see true and accurate results, would have to be 5, 10, 20 years plus potentially to actually see the long-term effects and migration of compound from these posts. So we're in a very early stage of this study, and we're not seeing very much movement. This isn't necessarily important, but I wanted just to show you that the detection limit in ppm, micrograms per milliliter, ppm, is very low, and a lot of them have asterisks. And I put the asterisks only next to the controls that are below the detection limit, so then you can compare that to the others. And this is the third depth. So upper core, middle core, and then third depth. We're seeing a little bit more, but the first thing you'll notice there is those error bars are huge. And that is because we had a single sample that had very high amounts of phenanthrene pyrene pricing and benzoate pyrene a little bit. But unfortunately, a single sample doesn't give us statistical significance. So we can't say for sure that there is a trend, but you can say there something's going on. And the causes of that can be highly variable. As I mentioned, we're having very low concentrations captured, 0.2 ppm, which is well below the EPA regulation limits for drinking water and groundwater itself. No clear trends based on height, distance, or species yet. And the outlier it makes the data look a little gross, but it is true and accurate to what we measured. On to the second study. Similar trend, we're seeing between 3 and 6 months. We're not seeing a significant difference, though it looks like there are a greater amount in the early stages as compared to the 6 month stages. These are both Douglas fir posts. And I'll be talking about the pine here in a moment. We'll see the same story. And that's, there's a high variation, which is innate to environmental sampling, a very common thing to see, and still no significant trends yet. All right, on to pine, same story, but we get a little bit of variation where we see the phenanthrene on the right there, 6 months, actually had a spike, which is, it goes against the trends that we've been seeing so far, of course. So despite that, the error bars are still very large. Similar issue with what I mentioned before, where a single sample had an extraordinarily high amount relative to the rest, or high concentration, I should say, relative to the rest. And finally, the soil field study. We noticed a lot of phenanthrene and pyrene within there are differences between phenanthrene and pyrene between the 3 and 6 months. And quite a bit, all of the heavy molecular weight pHs you can see are asterisked, which means they are BEL divided by 2. And this is important because I would say 90%, that I'm pulling out of my head, of the samples that are heavy molecular weight pHs are well below the BEL value. It's very rare that we actually can analyze or detect those due to the low abundance in the creosote we're using, as well as the detection limits, the lower migration patterns that they have, etc. Well, it looks like we're seeing a lot of pH here. We're still in the scale of 0.5 ppm, and around 0.3 is where we start to reach the regulatory limits. Again, very high error bars. Unfortunately, no obvious statistical differences here. And similarly with pine, we're getting not a lot in the first month, but we're seeing a little bit of variation from the second sampling time, 6 month time. And I should mention that these are 6 inches away from the post at the same point. Similarly, phantom and pyrene have the big variation that I mentioned, but not a lot else going on yet. So to conclude, we haven't seen a lot of statistical trends yet, but that doesn't surprise me or others because the longevity of these experiments tend to last much longer than the year that this data will be, or the 6 months this data is representing, but the 2 years that I'm in this project. So the trends can be greatly improved by elongating the project, as well as potentially increasing our detection rates in various concentrated steps, or using, for example, a rotary evaporator, which can allow the condensing of our concentrating of our target compounds while also retaining the solvents lost. As I mentioned, these high molecular weight pHs are poorly resolved. It's hard to tell, hard to see them, primarily because they already exist in very low amounts, and secondarily because of their migration, as I mentioned. So some future work that I would like to implement into this study is creating a little bit more bulk around the statistical modeling of the data that I have so far. Some analysis of variation will give us a little bit more certainty and statistical significance of the relative impacts of each of these factors here, the high distance soil type and species. So using ANOVA modeling will be very helpful in figuring out which is the most influential factor when it comes to this migration. And as I mentioned, this project will be extended after my initial 2-year span. And this will be very important for creating a well-rounded amount of well-rounded data for this project. And eventually given enough of the seasonal measuring of the water sample or water velocity, we'll be able to calculate the average concentrations of pHs within the water itself over the sampling period, and not a single time point. Something I wanted to mention is that the velocity measurements began a little bit late into the study, so this will be a progressive thing moving onward. So I thank you for your attention, and if you have any questions, please let me know. Yes, ma'am.
Yeah, so if you're looking at the 16 priority solutions, is it possible that there are other similar weight pHs coming out that you're not detecting, or is there any signal for that?
Absolutely, great question, because I did want to touch on that, and I'm glad you asked because I did not. There are a lot of compounds that are similar in weight, and the way we get around this is a lot of these compounds have unique reference ions that are associated when you break this down in the GCMS or during the mass spectrometry section. So they have a semi-unique fingerprint of reference ions that we reference using the GCMS, and we use this to give a little bit more certainty that the compound we're looking at is actually the compound we're looking at, not just a similarly weighted compound. Yes, thank you. Good question. History.
But I guess follow up on that, when you are sorting through these, mass spectra, do you see anything? Have you identified anything else coming out?
Oh, absolutely.
So examples of that.
I haven't actually, so there's a function on the GCMS called a similarity search, where you can look at the peak area that we get, and it takes into account the reference ions we chose to, and we can use this to compare against a bank of other compounds that we already know of. And this is typically done, but they're not as accurate for compounds that we don't necessarily know a lot about. And because there's 1,500 pH compounds, the vast majority of them haven't been studied very well at all. So a lot of this information is to be determined. Any other questions?
No. On your barrel study, I'm not sure I understood what the setup is, but it looked to me like you had 0 months, 3 months, 6 months, 12 months, 18 months. Is that, there's an assumption there that the leaching is going to be completely symmetrical. Is that a good assumption?
I would say it's an okay assumption. I feel like the lack of water movement that we see within the barrels will contribute to the lack of symmetric leaching in general.
So just, I would think about it for a second. So if you are measuring pHs coming off of the post, what does that do to the concentration of pHs in the post?
It's reduced.
So then what would you expect as time goes on?
Well, we would expect to see the pHs be reducing over time anyway. But in a confined area, those pHs don't really have a lot of place to go. We haven't seen an accumulation yet, but hoping with more sampling, we'll be able to begin to see that accumulation.
Yeah,
But they have to be. So you either have to assume that the leaching is symmetrical coming out of the post, or that once they get into the soil, they diffuse in the soil all the way around the post.
Sure.
Well, which doesn't make any sense because they would also diffuse away from the post, right?
Right. We are assuming that it's a homogeneous, me as an I am assuming it's a homogeneous migration from the post. Because really we can't really test otherwise within a confined system with no water movement.
well, it's a problem of the sampling, because once you take the soil out, you've disrupted that. You've already disrupted that area, so we've thrown this back and forth a bunch of times, and like you take a soil core and you can't put, like, if you put fresh soil back in there to replace it, you've already,
That's disrupting it.
yeah, and so it's kind of like, how do you look at this system without, or how do you make measurements without disrupting it? And I don't think there's really a good way of doing it.
Yeah, so of course it's not ideal because of that. But
Yeah,
best we have is to not disturb any future sampling sites, and that's why this method was created.
Okay. And for the poles that are in the river, is there an oil sheen?
There was not significant, but there was an obvious oil sheen when they were first installed. And after the, I want to say 6 months sampling, I didn't really see much of the sheen naturally undisturbed, but when you walk up close to it when you're sampling, the agitation of the water around will actually show a fairly faint sheen that comes off. Nothing that's very large that I would say in my experience. It tends to be a few feet or at most in any direction and will quickly leave the area. But yes, you tend to see more sheen off the pine as well.
So I'm sure you thought of this, but you didn't say anything about it. Why do you really need 1.5 mils to run the GCMS?
We use 1 mil, but no, it was more of an artifact of the concentrating steps that we did and the.
Yeah, why can't you concentrate it down to 0.5 mil?
We could, but
Then
the
you
issue
need
is
3 times.
it required 1.5 mils for our solid phase extraction to clean out any of the extra impurities. So we had to at least start there. I guess we could have gone on to.
But after that, you could take it down to
1.1-ish, 1.5-ish.
Yeah.
We have concentrating vials that we can put into those to analyze smaller volumes, but.
well, the concentration is a little uneven just with the way that we do it, so
We have a very simple method of concentrating these. We blow air, lab air across the samples to concentrate them, which is a very non-ideal way of doing it because we're losing a small fraction of the light molecular pHs, but we're also losing variable amounts of solvent. The solvents will off-gas unevenly as well.
I think Matt probably has more insight into how that method developed, but I think it's a throughput.
Oh, it's classic. Yeah, that's classic, except a lot of people use nitrogen instead of air. Since the air in this building is
Maybe dirty.
Yeah, we chose this method just because it was more easily accessible and able to implement with the thousands of samples that I have to extract and analyze. Using something like a rotary evaporator would be excellent, but they use very, very low throughput. So that would be a huge bottleneck.
There's no way. You can do that.
Yeah. So a lot of the study parameters have been weighing the differences between ease of use essentially and the throughput that we can produce with them.
We talked about using like the NV discs and things like that for filtering water or doing the filtration step, and, well, actually, no, it would be on the extract. But since these are the soil sachet method is. But I mean, that's also fairly low throughput and adds expense and all that stuff, so.
Yeah, it's just a scale of 3 different concurrent studies, we just had to make
It's not easy.
concessions.
Yeah, it's not easy to do this stuff.
All right, well, thank you guys for your attention. If you have any other questions, come talk to me after.